Hello class, welcome to this presentation, and this is going to be the last presentation in our course, and this will cover the discrete time sliding mode control. So this is a different paradigm altogether, but has the idea of sliding mode control in it, and we'll see how it differs from continuous time sliding mode control, and how so based on the differences, how the theory has been propounded. Now the material that I am going to cover is of course not the only material which is available in discrete time sliding mode control. It is a completely new or completely different domain of discrete time sliding mode control altogether. And what I will cover here will give you the basics to trade on this path, how the things has been thought of, and how we analyze the different theorems in discrete time sliding mode control, what exactly are we looking for, and these ideas have been taken forward, and the theory have developed. It's quite rich and vast, but we are only covering the introductory part of the discrete time sliding mode control. So if this can, like, discrete time sliding mode control can be a course in itself, but we are not doing that. We are only introducing the ideas, and with this we will have the end to the course of sliding mode control and observation for this particular semester. So since we didn't have regular classroom courses, one or two of concepts which I had covered in the last year, I am not taking those up because they might become a bit too much for you just to go through the slides and understand, and they are not good, like textbook is not available, so one has to read through the research papers, which might not be very suitable for all of you. So I am restricting from delivering the lecture from those one or two topics. So anyway, let us start with the discrete time sliding mode control. So what is the motivation behind proposing the discrete time sliding mode control? So why were we not satisfied with continuous time sliding mode control? That is what we have to first look into. So the first motivation is, of course, this well-known fact that previously, you see, in old times when there was a PID controller had been discovered and compensators were there, so we used to tune the parameters by dialing some knobs in a huge box, and inside the box there used to be a electrical circuit which was actually the controller. So everything was in continuous time. The entire controller was acting in continuous time. But as by the invention of the computer, what happened, one can take in the sensor data in the computer, do some computation, and then give out a control signal. And this became quite easy. One does not have to construct those large boxes containing electrical circuits, and did not have to dial knobs manually to set the parameters, to optimize the parameters. So one had everything done within a software system, and then from there only one can regulate, one can control the system. Things become easy. So from the computer, even there are microchips, microcontrollers are available, where one can simply write a few lines of code, and that performs the job of the controller. But what happened here, a shift came in the in the way that we used to perceive controllers. So previously the controllers, the hardware of the controller was there alongside the system and everything was running in continuous time. However, now what happened, the hardware of the controller is a digital electronics item, and it can only send its output values, or it can only update its output values after a definite time interval. So there is always a fixed or finite time which is required for the computation to be done, and then the value is whatever the output from the controller, that value is given out from that. So in this what is happening, the continuous time control action is changed to discrete time control action. So the control action is supplied to the system, or supplied to the actuator, with updates in every certain fixed amount of time. So this is one thing as has been written here. So the control calculation is done, so the computation happens in fixed time steps. And also the another fact is that the sensors had also become digital in nature. So they are not sensors which are like potentiometer and those stuff. There are some sensors, the potentiometers are continuous time sensors, but nowadays sensors are digital sensors. So they also measure the values, or the sample the output values, whatever they are measuring, they sample the output values only in certain fixed time points. So the output measurement is also happening in discrete time. So all this is leading towards a environment which is discrete time in nature, and in that environment we have to construct our controller. Next, what happened? What was the problem with continuous SMC design? So supposing that we have entire in continuous environment for sensor measurement is also happening continuously, controller updation can also happen continuously, but the unrealistic demand of continuous SMC was that if you think about the classical one, actually the discrete time sliding mode control originated while the classical sliding mode control theory was developing. It did not come after the higher order sliding mode control. So the problem that discrete time sliding mode control encountered was the infinite switching frequency problem, because as you know, the classical sliding mode control requires the control to switch with infinite frequency, so that the guaranteed robustness can be imparted to the system. While this is not always the case for higher order sliding mode control, as we have seen in super twisting, we can have continuous time smooth continuous time control action, but discrete time sliding mode control developed before super twisting came into being. So naturally the sliding mode control community was facing the problem of implementation of infinite switching frequency control action. So that was one drawback of continuous time design. And if we were implementing, then what was happening, we were actually implementing some high frequency switching which was not supported by most actuators. So the actuator wear and tear was happening, and due to this high frequency control action, there were unmodeled high frequency dynamics were getting triggered in the system, in the plant. So and this phenomenon is known as chattering. So this chattering problem was there. So all these were problems from the continuous SMC side, and along with this there was a demand for digital computation and digital implementation of control. So the community thought that let us go ahead with a formulation of discrete time sliding mode control and see how it can benefit the community, or how it becomes. So is it at all any different, or from the continuous time paradigm, or it is simply a discrete time application of the continuous time design. What I mean by discrete time application of continuous time design is that is it simply that you can develop the control action, you can, in theory you can develop the control action in continuous time, and when in practice you are supplying it through a digital computation microcontroller or something. So this is what normally happens to all controllers, like in PID or any other controllers that you work with. In the microcontrollers you have you write down the code, which is basically a control action for a continuous control action is getting coded there. However, it is only able to update itself in fixed amount of time. So this is some assumption that is undertaken. This is a practical scenario which what happens. However, for other controllers there is no such loss in performance or difference in the difference in the nature of in the behavior difference in the behavior of the system due to discretization of the control action. So this is what I am trying to stress here. So in most controllers there is no difference in behavior due to discretization of the control action. However, in sliding mode control, what the people saw is that if we discretize the control action, then there is a new behavior coming out of the system. So since there was a new behavior coming out of the system, so it demanded a thorough study of this thing from the very scratch. So it led to the field of discrete time sliding mode control, which is separate from continuous time sliding mode control. So it became a separate field because it had separate observations, it has separate behaviors of coming out of the system. So let us see what those things are. So as I am saying, it is not simply an extension of the continuous time system to the discrete time domain, as had been in most control actions, but this is not in that. What are the changes that happens that I have listed down here? So in continuous time system, the way the signum function is defined, as you know, is +1 -1, and at 0 any value between +1 and -1 is allowed in continuous time. That is the definition which helps us to impart the robustness, to cancel out the disturbance. So this definition is mandatory. However, in discrete time sliding mode control, this definition changes. Then in continuous time sliding mode control, there is this concept of eta reachability. In discrete time there is no such concept of eta reachability. In continuous time there is in continuous time we have finite time convergence of sliding variable. In discrete time we almost never have this. Almost never, why I say, I will just show you it. There is some possibility, but those are like very stringent possibilities. So normally it doesn't happen. And in continuous time SMC, the way the sliding surface design happens, So how it happens? If you remember, we have to design the sliding surface in such a way that the reduced order system is asymptotically stable, and for that our eigenvalues supposed to lie on the left half plane. So this paradigm changes in discrete time sliding mode control, and further the reaching laws which we had in continuous time sliding mode control, they also change. Okay, there are different reaching laws. What I mean by changes here is that there are different reaching laws. There is one reaching law which is a direct discretization of the continuous time one, but there are also other reaching laws which are quite independent of continuous time reaching laws. So among all this, like, what is the fundamental difference in behavior that is arising in continuous and discrete time is this. The fundamental difference is that the sliding variable never really hits the sliding surface with the switching reaching law. So in continuous time, you think about the classical case. In continuous time sliding mode control, we employ the switching reaching law with the idea, and what is why idea? It has been proved also mathematically. So if we had employed the switching reaching law, we found that the sliding variable would come, hit the sliding surface and stay there for all future times. But here, with a switching reaching law, we will never be able to, or almost never be able to, hit the sliding surface. And since hitting the sliding surface is out of question, there is also the staying in the sliding surface is also out of question. Okay, so how we can, you can see this, these are small steps you can see. So this is what the equation is simply a discretization of the switching reaching law. S dot equals to minus k sine s. So if you do a this is called the shift operator discretization, where your S dot is approximated by sk plus 1 minus sk divided by tau. So where tau is the length of the tau is the time period between two instants k and k plus 1. So here you see, here what happens. So the equation takes this form: sk plus 1 equals to sk minus tau capital K sine sk. And here if you see, we assume, suppose we start from any sk, then at every step what is happening at every step the value is decreasing by tau k, correct? So is there a possibility that sk plus 1 or sk can be 0 at some time? So the answer would be yes, but one has to carefully select this k depending on the initial condition S0. So if you know S0 definitely, then and you know the tau, then you can carefully select this capital K, so that at some instant of time your sk plus 1 becomes 0. Okay, so after that you have to maintain that 0 by stopping this switching function actually. Anyway, however, what happens that normally we don't know the initial condition exactly, and also the effect of disturbance and uncertainties are not considered in this case. So when such a thing happens, so normally we will not be able to land directly on the sliding surface by virtue of this equation. This is how the definition of the signum function changes, and here the definition is very simple. that at x equals to 0 we have sin x equals to 0. So the question of taking any value goes out of the window. So you have to be very definite here, what is the exact value. So you don't have a continuous stream of values there. How does a sliding surface design change? So in continuous time, the reduced order system poles were placed at the left half plane. Here also the concept of reduced order system poles is there, but since we are dealing with a discrete time system, the reduced order system poles have to be placed inside the unit disk. This we know from our control system courses, that if we have a discrete time system, then that system will be stable when the eigenvalues of the system matrix is within and is inside a unit circle. So the reduced order system poles have to be placed inside a unit disk. So now we come to the exposition of the discrete time sliding mode control, how it has been it has come into the literature. So the first attempt was made by Milosavljevic, and what he proposed is this. He proposed that whatever your sliding variable is, it must follow this law. So if you follow this reaching law, he said that your sliding variable will come towards 0. However, this ensures monotonous approach towards sliding surface. That is true, but there is a problem. So this may lead to a condition where your sk plus 1 in magnitude is greater than sk. When this will happen, suppose it is crossing the 0 line. So when the sliding variable crosses 0, then your sin sk plus 1 is negative of sin sk. So suppose your sk is positive, then this part is positive, and for this part to be negative, what one needs by suppose that this is 1, so this can be minus 0.5, that is also fine for this to hold true, but this can also become minus 2 or minus 3, and still this will hold true. So then you see that in the latter case, so this was 1, but this can be minus 2, minus 3, minus 4, no problem, still this will hold true. So but the problem is that you are crossing over to a larger magnitude than you already were. So you are actually diverging. You are diverging about the 0 line. You are diverging about the 0 line. So so suppose here is the 0 line. Then you are coming from this side and going here. Then you can diverge away. Then you can diverge away. Then you can again diverge away. So this possibility is there. Okay, in this reaching law. So this reaching law did not hold for much long, and Sharptooth corrected it. Sharptooth said that you simply restrict the magnitude. So the next step, the magnitude of sk plus 1 must be less than the magnitude of sk which is at this step. So in the next step, the magnitude must decrease from what the magnitude is in this step, and this is simply talking about the magnitude. So whether you are in the positive side or negative side, it doesn't matter. So if you are crossing from the positive side to negative side, still you have to have the magnitude less than what the magnitude was in the other side. So here the problem of divergence is taken care of, because it cannot diverge if it follows this law. So it ensures monotonous decrement even in case of 0 crossover. However, there is one problem here, which is one cannot actually calculate how close to the 0 the sliding variable can go. So there is no possibility of calculation of how close we are to the 0. So of course we are not reaching 0, but if we can have an idea of how close we are to the 0, then also that gives an idea, gives a measurement of the robust nature of the system, but that cannot be found in this case. So this is by Furuta, and if you look closely in Sabtuk reaching law and Furuta reaching law, they are actually the same. What Furuta did, Furuta extended the reaching law for, so the Sabtuk reaching law was for a scalar sliding variable, you can say. For Furuta extended it to a vector sliding variable. So even if this is a vector, then you can have a scalar function Vk formed, which is a Lyapunov function, and then what you simply need, this, your Lyapunov function must always decrease. So this is what is being said by this equation, and since the Lyapunov function is positive in nature, it always decreasing means it is always coming to 0. That means your Sk is always monotonically decreasing in magnitude. So this is what has been already been said. As for Sabtuk reaching law, the same thing holds here. Both the statements are same here for Sabtuk and Furuta. So here also we don't know how close to 0 the sliding variable goes. So what we now need, we have a formulation or some idea on how to assess whether the sliding variable is reaching towards 0. That idea we have, but we also need some concrete calculation of how close we are going to the 0. So let's see if that can be solved. Okay, so just before going to that measurement of ultimate of how close we are going to the sliding to the 0, this is one slide which aggregates all the new properties which we are seeing in discrete time sliding mode control. One has to remember these properties just to understand how discrete time sliding mode control is different to continuous time sliding mode control. The first property is that there is 0 crossover by the sliding variable. So the 0 crossover happens. So you see this picture, you will understand a bit better. So every time it is decreasing, and somewhere a 0 crossover happens. But since we are having if the Sabtuk reaching law or the Furuta reaching law, those things are getting maintained, then what happens, after crossing the 0, again it tries to come towards 0. So it may come, it may take 2 or 3 steps intermediate, but again at some point of time it will again cross 0. Then it will again come closer to 0. Maybe it takes intermediate few steps, but somewhere it will again cross 0. So in this way, such crossing and recrossing will keep on happening. Okay. So at best, what will happen? At best, the sliding variable will be bounded by some ultimate band. So here the concept of ultimate band is getting introduced. So the ultimate band, concept of ultimate band is there because we know that it will always try to come towards 0. So if it crosses 0, wherever it reaches, it will again try to come towards 0. So in that manner it will keep on crossing and recrossing. So the band within which it crosses and recrosses becomes the ultimate band. So this ultimate band, if we have a narrower ultimate band, I am sure that you are able to you will appreciate that if we have a narrow ultimate band, that will mean that I have a stronger robustness, because when I will have the exact robustness I will have when the sliding variable becomes 0, as in the continuous time case. But exact robustness I am not able to achieve. I am able to achieve s equals to 0 in a close proximity of the surface. So my sliding variable is in close proximity to 0, but exactly not 0. So how close I can go, how close I can come? So if my ultimate band is smaller in size, then it means that I am more tightly closed, tightly bound to the surface. I am not going away from the surface by a large amount. So this is the idea of ultimate band. So the in discrete time sliding mode control research, you will see a lot of research is interested only in the fact to propose certain reaching laws which keep on reducing the ultimate band. So that is one of the objectives of research in discrete time sliding mode control. So however, this one factor is obviously we are understanding the invariance to uncertainties is lost, because we are not able to be on the surface. That means we are not invariant to uncertainties anymore. So only if s was equals to 0, we were having the phenomenon of complete rejection of the disturbance. But since s is not 0, the complete rejection of disturbance cannot happen. So the invariance to uncertainties is lost. We are not having finite time stability of the sliding variable. At best, what we are having the bounded stability. So the sliding variable is bounded in the ultimate by the ultimate band. So that bounded stability we must try to ensure. Here, if your sk is delta, what would be your sk plus 1? It would not be delta, it would be minus delta. Please keep that in mind, because we are crossing recrossing. So if one side we are in delta, another side we would go to minus delta. So that is the steady state behavior. So this is the steady state behavior. So steady state behavior means in both in this side as well as that side we are reaching the same value. That is the steady state behavior. So in one side if we are at delta, then the other side will be at minus delta. So here if sk is less than 0, then this would be minus delta, this would be plus delta, and this would be minus. So here there will be a plus. So in both cases you can see by doing pen and paper that your delta would come out to be this. However, in the earlier case we did not consider the effect of uncertainty or disturbance. So if the disturbance or uncertainty is there in the system, then the reaching law should also contain a disturbance term, as we had done in continuous sliding mode control in the same way. So there must be a disturbance term. So the disturbance term is added as plus dk here, and dm is added with k tau. Dm is added with k tau, where dm is the bound of dk. So dm is the bound of dk, and the condition on 1 minus k tau and 1 minus q tau and k tau remains the same. They must be greater than 0. However, there would be some additional condition imposed that we'll see. Now just let us read through these lines. Once the 0 line is crossed for the first time, it is crossed at every successive time steps. Size of each zigzagging step is non-increasing and the trajectory remains within a specified band. These two are the conditions for quasi sliding motion. So the quasi sliding motion condition is not changed. However, the reaching law is changed. So we have to see what are the conditions on q tau and k tau which will guarantee this quasi sliding motion. The condition for quasi sliding motion or the zigzag motion. What is the condition? The condition is that sin sk plus 2 must be equals to minus sin sk plus 1, which would be equals to sin sk. So this sign and this sign must be same. However, the intermediate sign must change. That is what we are saying. If we have three consecutive samples, then the sign of the middle sample would be different, and the sign of the samples at the first and the last sample would be same. That is what we must have. So if we have to guarantee this sort of a condition, then we must look into sk plus 2. So you see, sk plus 2 is calculated from the same reaching law. So the reaching law for instead of k plus 1, so we have changed k to k plus 1. So sk plus 2 has become 1 minus q tau sk plus 1 minus dm plus k tau sine of sk plus 1 plus dk plus 1. Now sk plus 1 also is a reaching law. We know what is sk plus 1. Sk plus 1 is minus 1 minus q tau sk minus all these things, and this has been plugged in. So sk plus 1 is plugged in this, you see, in this equation. Sk plus 1 is plugged in. So when we do that, when we plug in sk plus 1 and keeping the idea that sine of sk plus 1 is minus sine of sk, so this equation will come about. So this is left for you to do on pen and paper. You must verify that this equation is coming. So what you need to do, you need to plug in sk plus 1 and you need to consider that sine of sk plus 1 is minus sine of sk. So these two things you have to consider. Then you will see that this equation comes out. So from this equation, what we are actually having, sk plus 2 equals to this. Now if the sine of sk and sine of sk plus 2 has to be same, and we assume them to be 1 for the purpose of proving getting this condition, supposing that these two signs are same and equals to 1, then we see the worst case scenario. So as we have already have an understanding of looking at the worst case scenario when we have proved the twisting and super twisting algorithms, so here also we do same thing. We look at the worst case scenario. What is the worst case scenario here? So by worst case scenario we mean that, okay, sine sk is 1 or sk is positive, but we will try to make sk plus 2 as low as possible, so as minimum as possible, and still it should be positive. So that is the worst case scenario. So we will try to make sk plus, assuming that sk is positive, we will try to make sk plus 2 as small as possible. Suppose even try to make it negative, but still it will be positive. That is the thing. So we will try to take the least values possible in this RHS. So whatever quantities in this RHS are variable quantities, we will try to take the absolute minimum of those variables. So here sine sk is already 1 because it is positive, but what I will choose this sk is a variable, is positive, it can take any positive value, but the least positive it can take is nearly 0. So we have assumed this to be 0. Then this is constant, dk and dk plus 1. We assume both dk and dk plus 1 to be minus dm, which is the extreme negative it can take. Even for these assumptions, we must have sk plus 2 greater than 0. So putting sk equals to 0, dk to be minus dm, dk plus 1 to be minus dm, whatever RHS is coming, that must be greater than 0. So if you do that, then you will see that this condition comes out from that inequality. So you do that in a pen and paper. What you have to do, you have to take this RHS, sin sk is 1, sk you put 0, dk you put minus dm, dk plus 1 you put minus dm, and this RHS you make it greater than 0. You just write greater than 0, and then you see what would be the inequality coming out like this or not. You have to only see what is dm less than something. So you will see dm is coming out less than this. So what does this mean? That this condition has to be satisfied by the reaching law parameters to ensure zigzag motion. So the condition here, by looking at it, it seems that the condition is on dm, but the condition is not on dm. dm is coming from the dm is the uncertainty which is actually related to the actual disturbance of the system. Okay, so dm can have any value, but whatever value dm will have, your qt and kt must together satisfy this condition, that q and k must have such values that this particular expression is greater than dm. That is what the condition is. The condition on the parameters are. Now added with it, we know that 1 minus q tau is greater than 0. Okay, that means q tau must be less than 1. So q tau must be less than 1. So actually what we have to do, we have to have the condition on k majorly. So k has to be perhaps made larger, so that this expression becomes more than dm. Okay. So this ensures the zigzag motion even in presence of disturbance. What would be the band, quasi sliding mode band? So now we will calculate the quasi sliding mode band now. So for calculating the quasi sliding mode band, what we have to do, we have what we are doing here, you see this is the expression. We are assuming sk less than 0 and very nearly equals to 0. Then we can have the extreme case. So how far it can go? So we are starting from the negative side. How far it can go to the positive side? That would be my band, that would be my bound, correct? So how far it can go? So if we keep this very negative, then it actually decreases the right hand side. So we are trying to increase the right hand side. We are trying to see how far in the positive direction it can go. So this has to be kept very low and almost 0, and your dk has to be taken as plus dm. So if you do that, and since sin sk is negative, you simply see that what is delta coming out. So this is having a value of delta now. So this delta will come out to be 2 dm plus kt, because this is 0 here, this is plus dm. So dm becomes 2 dm plus k tau, 2 dm plus k tau, and that is the value, that is the extreme value in the right hand side, which is delta. So sk plus 1 is delta. So delta equals to 2 dm plus k tau, and since there is a relationship of the dm with the parameters, if you put the dm less than that expression, you will see that this becomes less than k tau by 1 minus q tau. So the value of the parameters actually dictates the value of the ultimate band. And this also one thing to note, the value of the ultimate band is also related to the bound of the uncertainty, and it is more than twice the bound of the uncertainty. It's 2 dm plus kt. It is obviously more than 2 dm. How much it is more, that will be decided by what your k value is. So I hope you got how you are actually calculating the quasi sliding mode band here. So you are extremizing the right hand side to the maximum positive value it can take, while starting from a from the negative side. Obviously we have to start from negative side because sk and sk plus 1 are on two sides of 0. So if I have already assumed sk plus 1 is taking the maximum positive value, that means sk is negative, and to make this side maximum, sk is taken as 0 and sin sk is negative, so this becomes positive, and dk is taken as plus dn. So this is how we actually calculate the ultimate band given any reaching law. So if any reaching law is given, this is the idea of calculating the ultimate band. So we have to always check for the extreme cases to understand what would be the ultimate band. So in this is one approach of knowing the ultimate band. So Gauss reaching law is well understood, everything is proved analytically. We have proved that quasi sliding motion happens, that means zigzag motion happens. We have also calculated the quasi sliding mode band, but it also gave rise to questions in the mind of the researchers, and perhaps you also are having these questions. Do we really need the zigzagging motion? So this motion is imposed by Gauss, but do we really need this? So it has been seen later on that this actually limits the possibilities to arrive at a lower quasi sliding mode band. Next question is, do we really need the signum function? This does not serve any theoretical purpose anymore. In continuous control, there was a theoretical purpose behind using the signum function. The signum function was the one which actually imparted the robustness, but here it is not serving that purpose. We are not having any robustness. So that purpose is not getting served. So why unnecessarily keep the signum function? The next question is, we must focus on how we can guarantee a sliding motion, and not simply have a discretization of existing continuous time reaching laws. So the Gauss reaching law was a discretization of the continuous time reaching law. So it did not serve any purpose as such, and there may be other formulations which will make us close to sliding, or actually we might try to focus on how to guarantee a sliding motion. So this is how the bent of mind should have been. That is what they said. So all these drawbacks which we find in Gauss reaching law stem from the fact that it is a direct discretization of the continuous proportional plus switching reaching law. So if we do not do this direct discretization and devise fresh reaching laws without the continuous time design baggage, then perhaps we can do better. That is what is proposed. So let us see. The first one in that approach was the Utkin's reaching law, who simply said that let us simply do this: sk plus 1 equals to 0. So what Utkin has done? Utkin has forcefully made the next step of my sliding variable 0. That's all. So whatever is the reaching law, sk equals to some function of the states, you do sk plus 1. So you will have some control action coming in, and whatever expression you are having, you make it 0, and you will be able to calculate the control action. That is what he is saying. So in one step, the sliding surface will come to 0. So this is like deadbeat control. So one problem here is that the control energy might be too high if the system starts far away from the surface. That is one problem. but that problem can also be tackled by certain different formulations of the same Utkin's reaching law. And another reaching law is also following this, which also has a moderate control action, control energy that would be utilized. Now these class of reaching laws are called non-switching reaching laws, which does not have a switching signal in the right hand side. Okay, so the Gauss reaching law form the class of come in the class of switching reaching laws. So there are two types of reaching laws in discrete time sliding mode control. One are the switching reaching laws and another is the non-switching reaching laws. Whereas in continuous time, all reaching laws contain the switching term. They have to contain the switching term. That is the fundamental thing in continuous time reaching laws. They cannot do away with the switching term. But here in discrete time sliding mode control, there is an entire class of reaching laws which does not contain the switching term. So we can do without the switching term in discrete time sliding mode control. We only need to devise some suitable reaching law which brings me to the surface or close to the surface. Here you see we are directly coming to the surface, right? However, we have not considered the disturbance. I guess the next slide, the slide next to it is considering the disturbance. So what are the attributes of this? Sliding is exact, so exact sliding is possible. So I come to 0 and then I remain at 0 always. System starts sliding from the very first step. So wherever it is far away, it comes to 0, then remains at 0. So like this, you will see the graph. So if you plot this sk plus 1, this is very easy to plot. You take any sliding variable, okay, and you simply do sk plus 1 equals to 0. So it will come to 0 and it will stay at 0 from anywhere in the state space. But we have not considered disturbance. So if we consider the disturbance, then it looks like this. Then the disturbance comes in the right hand side, and then what happens? The system reaches sliding surface only when dk equals to 0, and the sliding variable assumes the past instant disturbance value. You see, sk plus 1 equals to dk, that means sk at this present right now is dk minus 1, the past disturbance value. So this is in one way also, this in one way observes your disturbance, right? This is a disturbance observer also. So the past value of the disturbance is getting observed, not the present value. So you can reconstruct the disturbance, but you cannot use it. You will not be able to use it, because you are only taking able to identify the past disturbance value. The control energy is still too high if the system is far from the surface. So next, what is the what is the QSMB? What is the quasi sliding mode band? So the band value is so what is sk bounded by? Sk is bounded by the bound of dk, so it is dm. So the bound is delta equals to dm. It is very easy to see. It is directly seen from the equation. So sk plus 1, what is the maximum value it can take? It can take dm. What is the minimum value it can take? It can take minus dm. So it is bounded by plus minus dm. So the delta is dm. So this is huge improvement from the Gauss reaching law, because Gauss reaching law was 2 dm plus kt. So it was twice the disturbance value plus some additional baggage. Here it is simply dm. So by moving from switching reaching law to non-switching reaching law, the robustness improves drastically, though there is no switching action in the system. So you see how different it is from the continuous time sliding mode control, where we cannot do without a switching action, but here if we remove the switching action, we are having better performance in one way. In terms of robustness, we are having better performance. In terms of reducing the ultimate band, we are having better performance. The next non-switching reaching law is this Bartosz-Ridge reaching law. So I had worked with this man, a very gentle person, and having a grandfatherly attitude to you. So he is very old, quite old, and very gentle, and very sharp and brilliant as well. So he proposed this reaching law. So this is called Bartosz-Ridge reaching law. So here what we are having, he had added a priori function to the Utkin's reaching law. You see, this part is Utkin's reaching law with disturbance. He has added a priori known function SDK, defined in this way, that if S0 is greater than 2 dm, then your SD0 should be equals to S0. That means that if the initial value of the sliding variable, sliding variable is greater than 2 dm, then the initial value of this a priori function, we choose it to be same as S0. Then SDK SD0 greater than equals to 0 for any k greater than equals to 0. This means that SDK, the entire evolution of SDK is in the same side as SD0 is in the same side of the 0 line. So that's why these two together becomes positive. So if this is negative, this is also negative. If this is positive, this is also positive for all k. For all k, this is in the same side of SD0. This is what it means. SDK equals to 0 for any k greater than some k star. So is identified some k star. So this must become 0 and remain 0 after a particular time instant k star. That means how it is evolving. So however it is evolving, it should come to 0 and then remain at 0. This function SDK, which is the a priori function. So after it becomes 0, this is same as the Utkin's reaching law, but before that it is different. And how it is coming towards 0, that is also said. He is saying that let us decrease this SDK plus this a priori function. At each instant it is decreasing by 2 dm. By 2 dm. This 2 dm is same as this 2 dm. Okay. So by a gap of 2 dm, it is decreasing. By a distance of 2 dm, it is decreasing. So there is decrement by 2 dm, and then it comes. Then there is some k star which we get, and from that k star instant it comes to 0 directly, and then it continues to be 0. That is how it is defined. So if, and another thing is that, so this is the evolution when S0 is greater than 2 dm, but if the S0 is less than 2 dm, then this is 0 always. That is what he is saying. Then SDK is 0 for any k greater than equals to 0. So what does this do? This actually brings down your control energy. So when your initial condition is 0 is quite far away, greater than this value 2 dm, then it decreases, then it makes this value decrease, and after some time it will become the Utkin's reaching law. And it becomes the Utkin's reaching law when we are less than 2 dm. If we start from this region which is less than 2 dm, which is a not very high value of S0, then it becomes the Utkins reaching law. So then in one step you can come to 0. That is what he is saying. So if you are not inside this 2dm, then you take some time to come to 0. So that is what the Bartoszewicz reaching law states. So this is what has been said here. You see, SDK converges monotonically and in finite time. SDK, not SK. SDK converges monotonically and finite time from its initial position SD0 equals to S0 to 0. So the convergence of this is directly to 0, but not this. Okay. In each step, SDK moves by a distance which is greater than 2dm. Then K star determines how long it takes for the system to reach the delta equals to dm vicinity of the sliding surface. So at K star this becomes 0. Then your S is bounded by only dm. So the bound is dm here also. The bound is dm here also, because after K star this will become 0. So the bound of S will become the bound of dk only, which is dm. The control effort is substantially reduced, and when starting sufficiently close to the sliding variable, it becomes same as the Utkins reaching law. This is what I was saying in the last slide. Also proposed one a priori function like this. So in the paper where he formulated this reaching law, he has also proposed an a priori function. So the a priori function is like this: SDK equals to K star minus K by K star is 0. So if we have a function like this and K star is less than S0 by 2dm, then all the properties that has been discussed by him is followed by this function. And you can see simply that what happens here, this is, so you take different values of k equals to 1, 2, 3, 4. This is simply coming as a fraction of S0. K equals to 1 is K star minus 1 by K star, then K star minus 2 by K star. Some fraction of S0 we are having. So some fraction of S0 we are having, and somewhere at when it becomes K star, then it drops to 0, and from then onwards it is kept at 0. Then onwards it is kept at 0. It's kept at 0. From K star onwards, this is not what it is followed. From K star onwards it is 0, like this. So the final part, so after knowing all these reaching laws and understanding how they behave, that is how they converge to the 0, whether they are having a zigzag motion, what is the ultimate band. When we have all this analysis done on a particular reaching law and satisfied that this is the behavior that we need, then comes the question of using this reaching law to design a controller, discrete time sliding mode controller. So for that, what we have to do, so we have to discretize the system equation first. So the system is given in like ABC format. If you have the linear time invariant system, ABC format, then we have to discretize that to form the discrete time linear time invariant system. And this discrete time linear time invariant system, if you do a regular transformation on that, it will come into this form. So the discrete time matrices are G and H. So A and B, AB transforms to G and H when you do the discretization. So how this discretization is done, these things are already covered in previous control theory courses, so I am not going into that. Even your MATLAB has functions which can convert your continuous time systems to discrete time, but what I will suggest is that you do a discretization using the shift operator approach. That is the best one. Why? Because if you do a discretization with the MATLAB operator, what will happen? Suppose your continuous time has matched uncertainty. That matched uncertainty will not remain matched in the discrete time formulation. So that is the problem that we'll face. But if you do a shift operator discretization, then your matched uncertainty will remain matched in the discrete time formulation also. So I suggest you do a shift operator discretization and then obtain the G and H from the shift operator discretization. So G and H, once you get, you can do a regular form transformation on G and H, and you will get a system partitioned in this manner. And from here, first what you have to do, you have to do a sliding surface design. So you take this C1 C2 C1 x1k plus C2 x2k, which is CT xk as usually you take, but and then the reduced order system will become like this. But now what you have to do, you have to place the poles of this system within the unit circle, not on the LHP, but within a unit circle. That is the difference. So once you have placed the in unit circle, so that will be done by choice of this C2 and C1. Normally C2 is taken as I, so C1 is what you are designing. So the same thing. Then when you have got the sliding surface, then you can calculate the control. And the control law design, for the control law design you have to go to SK plus 1. So this is CT xk plus 1, which is CT gxk plus CT h uk plus fk. This is a simple expression. And then you have to match this RHS with the reaching law. Match this RHS with the reaching law. So the Gauss reaching law, Sk plus 1 equals to 1 minus q tau Sk minus k tau sin Sk plus dk. So dk you have to take equals to Cth fk. Dk has to be taken as Cth fk, and then you can calculate what is uk by equating those two sides. This RHS and the RHS of the reaching law you can equate, and you will find what is what is uk. uk will come out to be this form. You can calculate this. You should do this. You should find out what is your uk. Do it on pen and paper. Then Utkin's reaching law. Utkin's reaching law, this is the RHS coming from the system, and from your Utkin's reaching law, Sk plus 1 is simply equals to dk, and Cth fk equals to dk. So your uk will be simply minus Cth inverse Ctg xk minus Cth inverse Ctg xk, this much. And in Bartos-Weak you do the same thing. You will see this a priori function is coming here additionally. So if this a priori function was not there, and in the event that it will become 0, then this control action will be same as this control action, but it will have this with it in Bartos-Weak. So this is a case, and this completes our discussion on sliding mode control itself. We will not have any further lectures, but there will be further assignments on discrete time sliding mode control. So the assignments will be in the form of verifying the Gauss reaching law and the Bartos' reaching law. Utkin's reaching law can be easily verified. You can do that if you wish. And then also formulation of the control strategies, so which is done in the last two slides, for the system that you are working with. So you are working with some system, you have to do a discretization of the system. You do a simple shift operator discretization, and then you make it regular form. You design the sliding surface so that the reduced order system is stable. You design your control action, you implement that control to the system and see whether everything is working or not. So that would be the assignment. I will formally write it down in the Google Classroom what you have to do, and then you submit those assignments. But on pen and paper you should verify all these equations that have been presented in this slide. I have not done step by step calculation of any of these equations purposefully because they are very easy to do. I have given you the idea of what we are doing, how the considerations that we have taken for deriving the or for doing the proof, or for deriving the ultimate band, all these things. So you put those considerations in your equations and you do it by your hand. It is simply a rearrangement of the equations, nothing else. Okay. So with this I say goodbye, and hopefully you are studying the course, and the materials are there. If it is difficult somewhere, you are not understanding, now is the time you can pose questions to me. So you write down in the Google Classroom in the thread, or you send a mail, whatever in way you want to communicate. So you pose the question, and if I have a few questions, then I can make another video or a presentation on those questions and address them. Okay, then so I am ending this course now. This is the end of the course, not just the presentation. So hopefully we will see each other when the institute reopens.